So we'll get into some vocabulary. So we have the vocabulary ready to go. And then on Monday, we can start with the examples. Okay. So matrices. If you guys have ever watched the movie The Matrix, has anybody ever seen that? Yeah, I see a few head nods. So in the movie The Matrix, there's like where all the numbers come down the screen, right at the beginning. It starts and all these numbers are scrolling down the screen. And they go over and over and over and over. And they're all like perfectly aligned. They're all in perfect rows and in perfect columns. And that, just like the name says, is a matrix. So a matrix is simply a rectangular array of real numbers. Okay, we put these square brackets here around a matrix that you can see in that example. That's how we kind of group together the numbers of the matrix. And then we have rows and we have columns in a matrix. So if I were to say that this one here, it has m rows and n columns. So here there are m rows, and then here there are n columns. Then one thing we can talk about is the order of the matrix. So the order, it's a vocabulary word. Make sure you know that term. And we say the order of the matrix is m by n. So for example, if I had this matrix, 2, -1, 3, 5, 7, -1/3. This matrix has 3 rows, so it's a 3 by 2 columns, 3 by 2. Okay, and that's the order of that matrix. All right, then we have square matrices. So rectangular array. Well, if the dimensions of the rectangle are equal, then that's going to make a square. You guys know all that from geometry. So if we have a square matrix here, that's when the number of rows and the number of columns equal each other. So m is equal to n. When we say the order of a square matrix, we don't have to say 2 by 2. We can just say 2. So if our matrix is a 2 by 2, we just say the order is 2. Or if it's a 5 by 5, we just say that the order is 5. And then in a square matrix, we have something called the main diagonal. The main diagonal is going to go corner to corner. Okay. In the example here, we don't have a rectangular unless m equals n, but we don't know. So we have A11, A22, A33, and so on. It's not necessarily going to go to, or it won't go to that corner unless it is square. And notice that on that diagonal, even there, each of the subscript numbers are the same. So let me just go back up to that for a second. So these two numbers right here, for example, the 3 and the 2, the 3 represents that it's row 3. The first number represents the row that it's in, and the 2 represents that it's in column 2. So the first number is the row, and the second number is the column. Okay. So let me see an example of a 3 by 3 written with that notation. So my first term is A11 because it's row 1, column 1. Going across that row, my second one would be A12, row 1, column 2. Then I would have A13, row 1, column 3. And then my second row would be A21, row 2, column 1. Then I would have A22, A23. My third row would be A31, 32, and 33. And this here is a 3 by 3. So it has order 3. And when we look at this main diagonal, the main diagonal goes from corner to corner. Each of the subscripts match 1, 1, 2, 2, and 3, 3. So there's some basics about matrices and just some of the vocabulary that goes along with the matrices. And then we're going to look at the augmented matrix. And an augmented matrix is going to relate to a system of linear equations. And that's what we've been studying. So how do we relate what we've been studying about systems of equations to these augmented matrices? And we're going to do some of these by hand, and then we're going to learn how to use our calculator in matrices to help us solve large systems of equations, which is going to be pretty fast and cool. So if I have a linear system, let's say I have 2x minus 3y equals 5, and x plus 6y equals negative 8. If that's my system, I'm going to write this system into an augmented matrix. So the augmented matrix means it's going to be divided. An augmentation means it's divided somewhere. There's a barrier. Okay? On the left side, okay? On the left side, so the left side is the coefficient matrix. All we do is we pull the coefficients. So a 2, a negative 3, a 1, and a 6. So we do 2, negative 3, 1, and 6. That's the left side. It has to be the left side, so I need something to be the barrier. So I'm going to put a vertical bar. I'm going to call this the augmenter. Augmenter. I just made that up. I don't even know if that's a word or if that even makes sense. But I'm going to call it the augmenter. Basically, it's just the divider between the left side and the right side. Okay. On the right side, then, it says we're going to write the constant matrix is on the right. So on the right of that, we're going to put the 5 and the negative 8. So I put a 5 and I put a negative 8 and put that into my brackets for a matrix. So this is now the augmented matrix that represents the system. Okay, so we've taken this system and we've written it into a new format called an augmented matrix. And that's how we can connect a system to an augmented matrix. Now we're going to continue on with what does that mean for solving? And in order to use this augmented matrix now to solve the system, we're going to go back to what we already learned, elementary row operations. So elementary row operations says we can interchange, multiply by a non-zero constant, add a multiple of one row to another, just like we've already learned earlier in lesson 7.3. Okay? We're going to learn how to apply those to this augmented matrix to get the final solution to the system. All right, we're going to continue on with